Everything we've seen so far has been for uniform circular motion, but now let's consider non-uniform circular motion. So remember, uniform motion is when an object is moving in a circle at a constant speed. That means our tangential velocity is constant, that's our speed, and our angular velocity is constant. This is the rate that we're completing a circle. This is constant if we're talking about uniform circular motion. Well, let's now consider non-uniform circular motion when the rate that this object is making its circle is changing. Like maybe it's a car driving in a circle and it's going faster and faster and faster and faster, 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 faster as it drives. Okay? Or maybe it's the ladybug sitting on the record player and the record is initially at rest and then you turn it on so it starts from rest and slowly starts to go faster and faster and faster until it reaches that final speed. While it's speeding up, that would be non-uniform circular motion. So let's talk about what happens in that case. If your tangential speed here changes, you have to have a tangential acceleration. That means you're going to have an acceleration. Let's say you're going faster. If this speed is increasing, you're going to have an acceleration in the same direction, in that same tangential direction, tangent to the circle. This means that this value is getting bigger. It's going faster and faster and faster. Well, if you're going faster and faster, your speed is increasing, your meters per second. If that's getting bigger, this value is also going to increase. Your angular velocity has to increase. The rate that you're completing a circle is going to increase. That means that there's some type of angular acceleration. And we're going to use the variable alpha. So this is another Greek letter. It's not an A. It's a Greek letter alpha. And alpha occurs whenever your angular velocity changes. You have an angular acceleration, and alpha measures your angular acceleration. Alpha measures how fast your angular velocity changes. So the way to calculate it, again, alpha is measuring how much did your angular velocity change by and how long did it take to change. So it's the rate of change of your angular velocity. Whenever you have an angular acceleration, you also have a tangential acceleration. And whenever you have a tangential acceleration, you also have an angular acceleration. These two things don't occur on their own. Just like, they're just different ways to describe what's happening. Just like describing the tangential velocity is just a different way to describe the fact that it's moving in a circle, and angular velocity is also a different way to describe that it's moving in a circle. Anytime an object is moving in a circle, you could tell me its angular velocity and its tangential velocity. If an object is moving in a circle and its speed is changing, you could tell me the tangential acceleration, and you should be able to tell me the angular acceleration. This acceleration measures how fast this value changes. This acceleration measures how fast this value changes. These two things are related. The tangential acceleration and the angular acceleration are related, just like tangential velocity and angular velocity are related. Here's the equation that relates tangential acceleration to angular acceleration. Our units for angular acceleration are just radians per second squared. So the one thing we have to be careful about with our angular acceleration is the sign, whether it's positive or negative. And it's going to be the same thing that if the angular acceleration is in the counterclockwise direction, we're going to consider that a positive acceleration. So let's consider a disk. It's spinning in this direction, and the rate that it's spinning is slowing down. So first of all, based on the direction that it's spinning, let's try to figure out whether its angular velocity, omega, is positive or negative. Well, this is spinning counterclockwise, so omega is going to be positive. But it's slowing down. The rate that it's spinning is getting slower and slower and slower. So what does that mean about alpha? Well, if it's slowing down, we want our acceleration to be in the opposite direction as our velocity, so that would be a negative alpha. Our angular acceleration would be negative. This would be accelerating in the clockwise direction. Let's look at this one. So here's an object. It's spinning like this. It's spinning clockwise. What can we say about omega? It should be negative because it's spinning clockwise. But it's slowing down. That means that we want the acceleration to be in the opposite direction of the velocity. So I'm going to say in this case the angular acceleration is positive. Don't think when something slows down that means the acceleration is negative. Remember, the rule is that when something is slowing down, the acceleration is in the opposite direction of velocity. That's the rule that I'm trying to preserve here. Let's consider this case where this object is spinning. It's rotating in a counterclockwise direction, so no matter what, the angular velocity is positive, but it's also speeding up, so it's spinning faster and faster and faster and faster and faster and faster. When we're speeding up, we want our acceleration to be in the same direction, so in this case my angular acceleration would be positive. And then finally we can do the last example where we are rotating in the clockwise direction, which means my angular velocity is negative, and I'm speeding up. That means I need an acceleration that's in the same direction, so I'd have a negative angular acceleration. Here's an example looking at angular acceleration and tangential acceleration. So press pause, think about it, and then press play to go over with me. Okay, so I'm being told, the object is starting from rest. There's our little beetle. He's still having a great time in his car. He starts at rest. 4 seconds later, he's traveling at a speed of 6 meters per second as he's driving around that perimeter of the clock. I want to know what's his angular acceleration and what's his tangential acceleration. Well, this value I've been told here, this is a tangential velocity. So if I think in terms of my tangential velocity, I can say he has a final tangential velocity of 6 meters per second. He has an initial tangential velocity of 0. It takes him 4 seconds to go from this tangential velocity to this one. So I'm going to be able to calculate my tangential acceleration. This is all just the same as a normal kinematic equation. These are the same type of kinematic variables. I know that if you start at 0 and 4 seconds later you're going 6 meters per second, no matter what, I know that you were accelerating at a rate of 1.5 meters per second squared. That's how you get from a velocity of 0 to 6 meters per second in 4 seconds. You have to accelerate 1.5 meters per second each second, or 1.5 meters per second squared. So now that I know the tangential acceleration, I can use this equation here to figure out my angular acceleration. So here I've plugged in my tangential acceleration and the radius of the circle the object is making, and I find that my angular acceleration is 3 radians per second squared. Okay, so this brings us back to kinematics. These are our kinematic variables that we've seen in the past. The s here just means that it could be x or it could be y. Or now we can talk about s as the the distance traveled around a circle even. So we're going to think of these as linear kinematics if we're just thinking that this is x or y. And now I can introduce a set of equations called circular kinematics. These are the equations we have to use if our object is accelerating, if it has a changing angular velocity. If the alpha, the angular acceleration, is not 0, I need to use these equations. If we're using uniform circular motion and alpha is 0, then I have the nice simple equation that's just this first piece that we've seen before. So these are going to be our new circular kinematic equations. We're going to use them in problems just like we used our linear kinematic equations. And then we have these equations here that relate kind of my normal variables, my tangential variables, a sub t, my tangential acceleration, v sub t, my tangential velocity, and s. S is like that arc length on the circle. It relates those to my circular variables, theta, my angular position, omega, my angular velocity, and alpha, my angular acceleration. So you can imagine we're going to be solving the similar types of kinematic problems that we've solved before, except now we're going to be looking at objects that are moving in a circle.